Open your books to page 264 as we move into lesson 62, continuing to work with radicals. You learned in lesson 6.1 a little bit about square roots and cube roots and how those things work. This is really a continuation of a lot of stuff you did back in your pre-algebra days. You should have done quite a bit with radical signs, but in any case, it's been a little while, so you're probably rusty. So make sure you keep reviewing those lessons or those rules that are in the book because it gets pretty sticky pretty quick. Okay, so lesson 6.2 is entitled Properties of Radicals, and what they are looking for us to do is to be able to simplify a radical to its simplest components. Okay, it's almost like factoring. When you were told to factor something, you want to get it to its simplest factors where no more factors other than one are shared in common. Well, we're not quite factoring. Well, there's a little bit of factoring involved, but we are looking for the simplest way to express something. And we're going to look at example 1, and I'm just going to break these down for you. If you are given the square root of 98, now keep in mind that the number under the little checkpoint is the radicand. The checkpoint symbol itself is called the radical sign. And if something is floating up here, it tells you what root they are looking for. If nothing is floating there, you can assume that it is a square root scenario, just like what we have here. We are looking for the square root of 98. Now, you might look at this and say, I don't think that's a perfect square, Mrs. Myers. No, but are any of its factors for perfect squares? Well, let's hunt around. The square root, or the number 49 has a perfect square root, so you can determine that whatever the square root of 49 is, multiplied by whatever the square root of 2 is, would indeed give you whatever the square root of 98 is. So hopefully you're kind of recognizing my process. I have something I'm searching for. I look for a square rootable factor. I break them up into two separate factors because really this is equivalent to this. Now, since I know the square root of 49 is 7, the final answer becomes 7 multiplied by the square root of 2. I cannot simplify the square root of 2 any further. It is not a perfect square. There aren't even any factors of it that are perfect squares. So it's as simple as that. Letter B, they have two cube roots for you. They say simplify the cube root of 25 multiplied by the cube root of 10. Incidentally, since they have the same index, they can be multiplied. If they didn't have the same index, they would not be able to. But we're basically able to multiply these because they have the same index. So you simply end up with the cube root of 250. That being said, like the above, we're not going to look for square root factors. We're going to look for cube root factors of this. And this is where you're going to get frustrated because you're going to say, I just don't know. Start listing out the factors. 1 and 250. Neither of those has a cube root. How about 1 and 250? How about 120 or 125 and 2? That happens to work. If not, 3 and something, 4 and something. Keep testing factors. You might have to list them out until you find one that is a cube. Okay? I have determined, and of course the book shows it to you, that the cube root of the product of 125 and 2 is the same thing as this. Okay? To the next level, we're going to say the cube root of 125 multiplied by the cube root of 2 indeed gives us the cube root of 250. Now that I have broken out the 125, he does have a cube root, right? Cube root of 125 is 5. Therefore, that comes out of the radical sign, and the end result, this is the cube root of 125. And the end result becomes 5 multiplied by the cube root of 2. There is no cube root for 2. Okay? There's no cube root for 2. Do not stress about C or D. We're going to get through these. So, starting with letter C, we're going to look at letter C. The cube root of this fraction, 81 over 8. Okay. Now, the first thing you want to ask yourself is, can I reduce this fraction? Can I simplify it to anything whole? You're not going to look for a mixed number. There's no use. And were this a 9, it would be perfect. 81 by 9. But it's not. It's 81 by 8. So you cannot simplify this in the form it's in. You have to then work it as the cube root of the numerator divided by the cube root of the denominator. Okay? So far, so good? Let's look for some cubic rootable factors. Okay? For 81, I know that the cube root of 27 multiplied by the cube root of 3 indeed will give us 81. Lucky for us, 8 is a perfect cube. 2 times 2 times 2. So the cube root of this is 2. Okay? Now, continuing on this, 27 is a perfect cube, whose cube root is 3. Okay, so I took the cube root of 8, made it the denominator, which is 2. This is simplified form of this. Okay, now the cube root of this is 3. 3, and 3 does not have a cube root. Okay, unfortunately, 3 does not have a cube root. So 3 times the cube root of 3 over 2 is the simplified form of the above scenario. So we pulled the cube root out, and it is multiplied by what is left. Here we pulled the cube root out. Okay, that's how we ended up with this answer. That's C. Finally, D. D is awesome. D is one of those examples where we can actually do some reducing prior to actually messing with it. Okay, the cube root of 60 over the cube root of 5 is the same thing as saying the cube root of 60 over 5. Notice from the above, I went from this to this because I couldn't do anything with it. Well, the same could be done in reverse. I can go from this to this because, look, 60 divided by 5 gives us the square root of 12, which is much simpler to work with. Okay, that's the simplified version so far. Now, let's look for perfect square factors because we're not looking for a cube, we're looking for square. 1 and 12, no. 2 times 6, no. 4 times 3, yes. That means the square root of 4 multiplied by the square root of 3 is the next step. That is a perfect square. It comes out of the radical. 2 multiplied by the square root of 3. Okay, is the simplest form for D. Can't go any further than that. Okay? Now, in example 2, just because I add variables to this scenario, it does not change anything, but you do need to recognize when variables have powers that it is slightly different than numeric powers. So we're going to go over that here real quick. Example 2. So A, the square root of 2 times A squared times B. Okay? Within this mess, I know that A squared is a perfect square. Okay? Whether A is a positive or a negative, I know it's a perfect square. So I can separate this into the square root of A squared multiplied by the square root of 2 times B. Neither of these has a square root. Okay? The square root of A squared is A. Okay? The square root of A squared is A. But it has to be the absolute value of A, because in order for this to be have a square root, it has to be whatever A was its absolute value, which is going to be a positive number. So even if A is a negative number, the absolute value is positive, and that is required because when you square something, the end result is always positive. Okay, so that's why I have this like this. Whenever you have the square root of a variable, it's the absolute value of that variable. A little bit tricky. I'm not real worried about it, to be honest with you. Okay. For the most part, if you wrote a radical 2b, I'm going to be okay with it. Simply recognize that if you solved it and you came up with a radical 2b, technically it should be this, but for your and on your compass test it would look like this. Don't think you're wrong. This is the correctest version, okay? Because again, the result of something squared is a positive. This could be a negative number, okay? We don't know. It just says A. Okay, you always want to have that radical to be very, very clear about what you're working with. Okay, letter B, 36w cubed square root. Square root of 36w cubed. Now you're going to say to me, well, w cubed does not have a square root. You're not quite right. Okay, so we're going to look for the square root of 36, which is 6. Would y'all agree with me? Let's not write that out, okay? And we are going to look for a way to make this have a square root. Well, if I break it up into w squared and w, which is w cubed, then this has a square root, okay? This has a square root. 6w radical w is what you're left with. Now, like the scenario above, since we know that the square root of 36 has to be a positive 6, you don't have to insert that absolute value symbol, which they describe there right below the answer in your book if you want to read about that further. Example C, okay, the cube root of x to the 5th over the cube root of y squared, or y cubed. So the starting thing has everything under the radical. We're going to break that up here in a minute. I'm going to write it their way to start with, x5, y3. So it's the same thing as saying the cube root of whatever we can do here and the cube root of that. Okay. Remember that when you're dealing with exponents, with variables, you simply want to look for a 3. X cubed times x squared's cube roots would give us that. Okay? And the cube root of y cubed is simply y. We've already simplified that one. The last bit we're going to simplify then is this. And just to kind of keep it clear, if you don't do these every single steps, some of you are going to see it right away, that you're going to pull out x, and you're going to be left with the cube root of x2. Because if you cube x, it goes back underneath and combines with this and gives you that. Some of you are going to see that right off the bat. Not all of you, I don't care. Just do the steps that you feel most comfortable with. I'm trying to do it as simple as possible. But, you know, again, your way is going to be the best way, whatever way speaks to you. All right, letter D. Letter D, the square root of 4 times A squared, awesome, plus 4 times B squared. Okay, you're looking at this going, well, wait a second, Mrs. Myers, how am I going to do this? Okay, let me just quickly show you the mistake you're going to make. You're going to want to say it's 2a plus 2b, okay? 2a plus 2b, and that looks like it would be right as a square root, okay? Awesome. But remember, if you square this, you're going to end up with 4a squared plus 8ab plus 4b squared. And that is not what this is. Okay? We're going to break this up into 4 and multiplied by a squared b squared. Okay, this is not a perfect square because this is a singular chunk. Just like you can't take this and turn it into that as the square root. 2a plus 2b is not the square root of this. If you square it, like I just showed you, you'd end up with 4a squared plus 8ab plus 4b squared. And that does not equal that, which is why this is not the square root. You can, however, factor out your 4 and you come up with 2 radical a squared b squared, because there is nothing you can pull out of that chunk a squared b squared. It is a singular unit. Just like you couldn't factor it in the normal universe, because this does not share anything, you can't root it either, even though it looks tricky enough that they want you to root it. Okay, now, right below example 2, there's a paragraph saying something to the effect of rationalizing the denominator. Now, what this means is, unfortunately, you're going to have scenarios where a denominator does not have a root, okay, whether it's a square or a cube. So if you multiply that denominator by itself in whatever form it was in, you will rationalize the denominator, which would be you have removed the radicand. Now, rather than me continuing to babble at you, I'm going to go ahead and show it to you. Okay, they don't exactly show it very well. So, A, radical 5/3. Now, as I said to you earlier, I'm like, okay, radical 5 over radical 3. Find the square root. There is nothing. So you're going to think I'm done. There is no way to simplify this. This is in simplest form. Fortunately, that is not true. Okay? The rationalizing the denominator thing in bold means you cannot have a radicand in the denominator. So to eliminate that, we multiply it by itself. And whatever we do below, we do above, just like renaming a fraction. Okay? The square root of something times the square root of something is whatever the something was, leaving without the radical sign, leaving me with that. Whoops, made a mistake there. Hold on, I'm going to stop right there, make sure I'm not making a mistake. Hang on.